Welcome to the deep dive.
Hey, great to be here.
So today our mission is to decode the hidden mathematical engine that basically keeps artificial intelligence from going completely off the rails.
Yeah, it's an absolutely crucial concept.
Right, and we are looking at a single, highly comprehensive Wikipedia article for this. It's simply titled Regularization in Mathematics.
Which sounds intimidating, I know.
Oh, totally. But we are going to translate all those dense formulas into the actual real-world mechanisms that make modern AI useful for you.
Exactly, because without this, AI is kind of useless.
Right. Okay, let's unpack this, because to understand why regularization matters to you, you really have to understand the fundamental flaw in how machines learn.
They have a major blind spot.
Yeah. So imagine you're studying for this massive, life-changing exam, but instead of actually learning the underlying concepts, you just memorize the exact wording of every single practice question.
I mean, you would probably absolutely ace that practice test, right? You get a perfect score because you know the exact answers to those specific questions.
Exactly. But then you sit down for the actual exam, and the wording of the questions is slightly different.
And you completely fail.
Right. You didn't learn how to solve the overarching problems. You just memorized a highly specific, static set of data.
And that is the ultimate trap for any learning system. We all naturally gravitate toward the comfort of knowing exactly what is in front of us.
Sure.
But when you step into the world of machine learning and statistics, that exact same trap is the single biggest hurdle to building artificial intelligence that actually functions in reality.
Because the AI just wants to memorize everything. Right?
Exactly. We're looking at a scenario where algorithms naturally want to become massive memorization machines. The technical term for this is overfitting.
Overfitting. Okay, so the AI is just memorizing the practice test. But the Wikipedia text gives us a core definition of how to fight this.
It does.
It says regularization is a process that converts the answer to a problem into a simpler one. But I gotta say, the idea of forcing a highly advanced supercomputing algorithm to intentionally be simpler, it just feels counterintuitive. I mean, shouldn't we want the most complex answer possible?
If we connect this to the bigger picture, it really comes down to the gap between what an algorithm sees right now and what it will eventually encounter out in the real world.
Okay.
In any learning problem, what we really want to minimize is the expected error over all possible inputs.
Meaning, like, how it performs out in the wild.
Exactly. How it handles data it has never, ever seen before.
Right, the actual exam, not just the practice test.
Yeah, but the problem is that expected error is practically unmeasurable. I mean, we don't have access to all possible future inputs.
Obviously not.
We only have a limited set of training data. And that data is, it's always measured with some amount of noise or errors or random fluctuations.
So it's messy.
Very messy.
Yeah.
And because the model can't measure expected error, it has to rely on what is called empirical error.
Which is what exactly.
It's just its error rate on that specific limited training set.
Gotcha.
So without any boundaries, a highly complex neural network will just bend over backwards to achieve zero empirical error.
It'll just twist itself into knots to perfectly hit every single data point.
Exactly. Meaning it ends up memorizing the random noise.
Oh, so it overthinks it.
It overthinks it completely.
Yeah.
And that's where regularization comes in. It introduces a mathematical penalty to stop that overthinking.
Okay, so it steps in and says, hey, stop it.
Pretty much. By forcing the model to be simpler, it reduces the generalization error, which is the measure of how well the algorithm adapts to unseen data.
So it essentially tells the machine, don't worry about being perfect on the training data. Worry about being robust for the future.
That's a great way to put it.
Okay, so it's basically giving the algorithm some strict boundaries. Now that we understand why models need these constraints, how do we actually apply them?
Well, the source breaks this down into two main philosophies. You have explicit and implicit regularization.
Okay, let's start with explicit.
So explicit regularization is whenever you directly add a concrete mathematical term to your optimization problem.
That's a literal rule.
Yeah, you are imposing a literal cost on the optimization function. Think of it as a penalty fee.
Oh, like getting a ticket.
Exactly.
Yeah.
The algorithm wants to minimize its error. But if it gets too complex, you slap it with a mathematical fine, which forces the optimal solution to be simpler.
Makes sense. And implicit.
Implicit regularization encompasses, well, basically everything else.
Like what?
This includes using a robust loss function, or throwing out outlier data points, or using ensemble methods like combining multiple decision trees into a random forest.
Right.
It's ubiquitous in modern machine learning, especially when you're training deep neural networks with stochastic gradient descent.
I want to push back on one of the implicit methods mentioned in the text, though, because it talks about something called early stopping.
Ah, yes, early stopping.
And the definition given is that you simply halt the training process when the model's performance on a validation dataset starts to get worse.
That's right.
Wait, so simply turning the algorithm off before it finishes its run is considered a mathematical technique. I mean, isn't that just giving up early and hoping for the best?
I know. It definitely sounds like you're just pulling the plug.
Right.
But mathematically, early stopping is rigorously viewed as regularization in time.
Regularization in time.
Okay. Intuitively, a training procedure like gradient descent, it starts with a very simple function, and then it learns more and more complex functions as the iterations increase.
Oh, I see. So by limiting the time parameter, like the number of iterations, we restrict the model's complexity.
Exactly, you're cutting it off.
So you're stopping it before it has the time to start memorizing the useless noise.
Yeah. And the text provides a fascinating theoretical motivation for this using least squares optimization.
Okay, hit me.
So if you consider the finite approximation of the Newman series for an invertible matrix.
Well, hold on. Newman series. Invertible matrix.
Too much math.
Yeah, let's translate that for someone who doesn't dream in calculus. Like, why does stopping early act like a mathematical formula?
Fair enough. Let's break that down. A Newman series is essentially an infinite sum, a bit like a Taylor series, but for matrices.
Okay.
In machine learning, finding the absolute perfect set of weights often requires calculating the inverse of a massive matrix of data.
Which is hard to do.
Right, and calculating that exact inverse perfectly is a recipe for memorizing noise. So the Newman series lets us approximate that inverse by adding up terms one by one.
Got it.
But each term you add makes the model more complex. So by limiting the iterations, which is represented by a time parameter, TU are essentially cutting off that infinite sum early.
Oh, so you get a good enough approximation of the solution before the model starts adding in the highly complex terms that represent all that noisy data.
Exactly.
It's like taking the test away from the student right when they've grasped the broad strokes before they start overthinking and second-guessing every single answer.
That's exactly what it is. And the text uses a really great visual example to illustrate this underlying philosophy.
Occam's razor, right.
Yes, Occam's razor. It describes a graph with a green function and a blue function.
Okay, picture a graph.
Right, and both functions perfectly hit all the given data points, meaning they both incur zero loss on the training data.
So they both get 100% on the practice test.
Yep, but the blue line is incredibly squiggly. It hits every point, but it fluctuates wildly up and down in between them.
It's all over the place.
Exactly. While the green line is a smooth, simple curve.
So regularization mathematically induces the model to prefer the simpler green function.
Yes, honoring Occam's razor. Because the smooth curve is just far more likely to generalize better to an unknown distribution of data.
Because simpler is better. Okay, but early stopping is an implicit method, right? It relies on manipulating time.
Correct.
What if we want to actively force a model to be simple through those explicit mathematical penalties you mentioned earlier?
Well, then we have to look at how we measure the complexity of the model's weights. The text introduces two primary methods for this, L1 and L2 regularization.
L1 and L2.
Yeah. L1, which is also called lasso, adds a penalty to the cost function based on the absolute value of the model's coefficients.
So it looks at the sheer size of the weights.
Right, and it penalizes the model for having too many of them. Mathematically, this penalty induces what we call sparsity.
Okay, here's where it gets really interesting. Sparsity means it forces a lot of the weights to become exactly zero.
Yes, it zeroes them out.
To wrap our heads around this, imagine an AI model is packing for a trip. L1 regularization is the ruthless minimalist who forces you to throw away 90% of your clothes, bringing only the absolute essentials.
I love that.
It basically decides certain features of the data are completely irrelevant and tosses them out.
A perfect analogy. Now, contrast that ruthless minimalist with L2 regularization, which is also known as ridge regression.
Okay.
Here, the penalty is based on the square of the coefficients.
Oh, so L2 is the meticulous organizer. It doesn't necessarily throw things away, but it makes sure everything you do bring is packed evenly in small, manageable bags so the suitcase doesn't burst.
Right, because it's squaring the weights.
So it punishes really large waste much more severely than small ones, right?
Exactly. Squaring a large number makes it exponentially larger, which results in a massive mathematical penalty. So L2 encourages the model to have smaller, more evenly distributed weights.
That makes total sense.
And the text notes that L2 is heavily tied to Tikhonov regularization, named after Andrei Nikolaevich Tikhonov.
Okay.
And unlike some really complex neural network math, Tikhonov regularization for a least squares problem can actually be solved analytically.
Meaning there is a single exact mathematical answer you can calculate?
Yes, you can write it in matrix form and find the exact optimal weights just by setting the gradient of the loss function to 0.
But there's a catch, isn't there?
There is a catch. During training, this algorithm takes O of d cubed plus n times d squared time.
Okay, let me jump in again. O of d cubed, you're talking about big O notation, right? The computational cost.
Big O notation.
Explain why squaring those coefficients suddenly makes the computer work so much harder.
Well, big O notation describes how the runtime of an algorithm scales as the data grows. The D there stands for the number of dimensions or features in your data.
Right.
Because finding that exact mathematical answer requires a process called matrix inversion, the math just gets incredibly heavy.
How heavy?
Well, O of d cubed means if you double the number of features your AI is analyzing, the time it takes to compute, the answer doesn't double. It multiplies by 8.
Wow, by 8.
Yeah. So if you have a massive data set, that L2 analytical solution becomes a massive computational burden.
Which is why we need algorithms that approximate the answer.
Exactly.
But, abstract map aside, what's amazing is how these penalties translate to real life.
What's fascinating here is the real-world value of that L1 sparsity we just talked about.
The minimalist packer.
Right. The text highlights this brilliant application in computational biology.
Okay.
Imagine you are developing a predictive test for a disease. You might have 10,000 biological markers you could theoretically test for.
But requiring a patient to undergo 10,000 individual lab tests is insanely expensive.
And totally impractical.
Yeah.
But by enforcing a sparsity constraint using L1 regularization, the algorithm looks at all 10,000 markers, realizes most of them are redundant, and ruthlessly forces their weights to 0.
It just throws them out.
It throws out the noise
Yeah.
and identifies the tiny handful of critical markers, maybe just 5 or 10, that actually matter.
So you get a simple, cost-effective medical test that maximizes predictive power.
Exactly. It literally finds the signal in the noise.
That is amazing.
Ah.
But the text mentions a bit of a catch with L1 too, doesn't it? A technical hurdle regarding how we actually define sparsity.
Yeah, it drops a great technical nugget. The most mathematically sensible way to enforce sparsity isn't actually L1. It's something called the L0 norm. The L0 norm doesn't look at the size of the weights at all. It simply counts the number of non-zero elements.
Oh, so it is the purest form of counting your luggage.
Exactly.
Yeah.
But solving an L0 regularized learning problem has been mathematically demonstrated to be NP hard.
NP hard, basically meaning it's practically impossible for a computer to solve in a reasonable amount of time if the data set is large.
Exactly. To solve L0, the computer would have to test every single possible combination of keeping or throwing away features.
Which, for 10,000 biological markers,
is an astronomical number of combinations. It is computationally intractable. So L1 is used as what mathematicians call a convex relaxation.
Convex relaxation. Okay, I'm going to need you to untack that one too.
Sure. So imagine the optimization landscape, like
Right.
the map the AI uses to find the lowest error, is incredibly bumpy and filled with jagged valleys.
Okay, a bumpy map.
That's the L0 landscape.
Yeah.
A computer gets stuck there very easily, but a convex relaxation smooths out all those bumps, turning the landscape into a single, smooth, giant fold.
Oh.
L1 creates that smooth bowl, making it incredibly easy for the algorithm to slide down to the bottom and find a solution that approximates the impossible L0 norm.
That is a brilliant workaround.
It really is.
But L1 isn't flawless either, right? Because the text points out that if you have input features that are highly correlated, like 2 biological markers that always show up together, L1 might just randomly pick one and throw the other away.
Yeah, which can make the model unstable.
Right.
It can.
Yeah.
Which is why we use something called elastic net regularization.
Elastic net.
It literally combines both the L1 and L2 penalties into a single equation.
Oh, best of both worlds.
Exactly.
Yeah.
It gives you the ruthless sparsity of L1, throwing out the useless features, but the meticulous L2 component ensures that highly correlated features get assigned equal weights.
Creating a grouping effect so you don't lose valuable context.
Nailed it.
Okay, so tweaking the weights works beautifully for basic linear equations. But modern AI uses deep neural networks with millions of interconnected nodes.
Right, much more complex.
You can't just shrink weights in a web that complex, can you?
Well,
Let's shift and look at the architecture of the models themselves. Because the source talks about an implicit technique used in neural networks called dropout, and I gotta be honest, this absolutely blew my mind.
dropout is wild.
During training, dropout repeatedly ignores random subsets of neurons. Like you are intentionally blinding the network. You make a system smarter by randomly giving it selective amnesia.
It sounds chaotic, right? But the mechanical logic is actually brilliant.
How so?
In a deep neural network, neurons can start to rely way too heavily on each other. If neuron A always corrects the mistakes of neuron B, they create this complex co-adaptation that only works for that specific training data.
They become a clique.
Yes, a click. So by randomly dropping neurons out of the network during a training pass, literally temporarily erasing them and their connections, you force every single neuron to learn how to be useful on its own.
Because a neuron never knows which of its coworkers are going to show up to work that day.
Exactly. If the neuron responsible for detecting a cat's ear drops out, the rest of the network has to work harder to identify the cat based on its tail or its whiskers.
The mechanism completely shatters those co-adaptations.
It does. And mathematically, dropout simulates the training of multiple different neural network architectures at once.
Because it's constantly changing shape.
Right. Because the structure is slightly different in every single training iteration. The final model is essentially an average of all these thousands of subnetworks, which vastly improves generalization.
That is incredibly clever. But dealing with these complex structures and mathematical penalties brings up some major computational hurdles, too. The text mentions a specific issue with computing L1 involving calculus.
Ah, yes. The infamous L1 kink.
The kink.
Remember how L1 uses the absolute value of the weights?
Yeah.
Well, if you graph an absolute value function, it looks like a perfect V. It's convex, it forms a bowl, but at the very bottom of the V, at exactly 0, there is a sharp corner. A kink.
And if I remember high school math, calculus hates sharp corners.
Calculus absolutely hates sharp corners. Gradient descent relies on calculating derivatives, which are essentially slopes.
Right.
At a smooth curve, you can easily calculate the slope, but at the exact pointy bottom of a V, the slope is undefined.
It's just a point.
Exactly.
Yeah.
The function is not strictly differentiable at that point, meaning standard gradient descent breaks down completely.
So how do you fix it?
Well, to solve this efficiently, the text notes we use proximal methods.
Proximal methods. Okay, how does a proximal method smooth out that kink? How does it bypass a mathematical impossibility?
So instead of trying to calculate the slope of the whole messy function at that sharp point, a proximal method splits the problem into 2 distinct steps.
Okay, 2 steps.
First, it performs a standard gradient descent step on the smooth, easy-to-calculate part of the loss function, basically ignoring the L1 penalty for a microsecond.
Just pretending it's not there.
Right. Then it applies a proximal operator to project that result back into the space permitted by the L1 penalty.
Okay, give me a physical analogy for that. Because my brain is straining.
Sure. Imagine you are walking down a valley, trying to reach the absolute bottom, but the very bottom is a dangerously sharp spike.
Okay.
Instead of stepping directly on the spike, you step slightly to the side where the ground is smooth.
Smart.
Then, the proximal operator acts like a mathematical magnet. If your step lands close enough to the spike, it just snaps your position directly to the center, precisely to 0.
Oh.
Yeah. For L1, this operator is effectively a soft thresholding function. It evaluates the smooth slope, and a weight is small enough, it elegantly forces it precisely to 0, bypassing the need to ever calculate the impossible derivative at the kink.
That is so elegant.
It really is.
So we've covered a lot of ground on how a single model learns from isolated data, but the source material pushes into more complex territory.
It definitely scales up.
What happens when we have complex systems analyzing interconnected tasks, or worse, data without labels? I mean, gathering labeled data is incredibly expensive in the real world.
It's the bottleneck of AI.
Right. If I have a database of 1 million pictures of cats, but I only paid a human to label 10 of them as cat, how does regularization help the AI figure out the rest?
Well, that brings us to semi-supervised learning. You have a tiny bit of labeled data and a massive amount of unlabeled data.
Okay.
The text outlines how regularizers can actually guide the learning algorithm by respecting the hidden structure of that unlabeled data. Use a symmetric weight matrix and something called a graph Laplacian matrix.
Laplacian matrix? That sounds intimidating. Explain that for someone who doesn't build supercomputers for a living.
Honestly, it's just a way to represent a web or a graph, mathematically.
A web.
Imagine all your million pictures are nodes on a giant spider web. The Laplacian matrix just maps out how tightly connected every node is to its neighbors based on their features.
Okay, I can picture that.
The regularizer relies on a simple intuition. If a distance metric tells us that two input points are very similar to each other, meaning they are close together on the web, then the regularizer enforces a massive penalty if the model predicts vastly different outputs for them.
It's guilt by association, but for math.
Exactly.
Think of it like a rubber band network. If an unlabeled picture looks mathematically similar to one of my 10 labeled cat pictures, the rubber bands pull them together.
Yes.
The regularizer gently forces the model to treat the unlabeled picture like a cat because it's caught in the same part of the web.
And the beauty of this is that the unlabeled part of the function can actually be solved analytically using the pseudo-inverse of the Laplacian submatrices.
Meaning?
You are calculating the reverse paths on the graph to seamlessly propagate those 10 labels across the entire million-picture dataset.
Mind-blowing. So what does this all mean for you, the listener, in your daily life?
It affects everything.
The text gives a fantastic real-world example of this interconnected math, and it has to do with how we binge-watch television.
Multitask learning.
Right.
Sometimes instead of solving one isolated problem, you want to solve multiple problems simultaneously because the tasks are inherently related. You want to borrow strengths from that relatedness.
Makes sense.
The text introduces a concept called clustered mean-constrained regularization.
Clustered mean-constrained regularization. Say that 3 times fast.
It is a mouthful, but the application is something everyone interacts with. Netflix recommendations.
Ah, Netflix.
Think of predicting what movie one specific user will like as a single, isolated task.
Okay.
Netflix has hundreds of millions of users, so they have hundreds of millions of simultaneous tasks.
And predicting my incredibly niche movie tastes is a single task. But I'm not entirely unique. I belong to a cluster of people who, say, love gritty sci-fi thrillers, but absolutely hate romantic comedies.
Right. The text explains that a cluster corresponds to a group of people sharing similar preferences.
Okay.
The clustered mean-constrained regularizer enforces a mathematical penalty if the function learned for your specific profile strays too far from the overall average function of your cluster.
So it's regularizing my recommendations by tethering them to the people mathematically similar to me.
Exactly. It enforces similarity between tasks, meaning users, within the same cluster. This captures complex prior information about human behavior.
Like shared tastes.
Yeah. If 10 people in your cluster loved an obscure new sci-fi documentary, the regularizer ensures your predictive model borrows that strength. It penalizes the algorithm if it doesn't recommend that documentary to you, because doing so would deviate from the cluster's mean.
So the math of regularization is literally actively shaping what you and I choose to watch on a Friday night.
It really is.
That is wild.
It's everywhere.
If we take a step back and synthesize this whole journey we've been on, regularization is clearly not just an obscure calculus trick for statisticians. It is the fundamental principle of preventing artificial intelligence from becoming an obsessive overthinker. It stops AI from memorizing the practice test. Whether it's the ruthless minimalism of Lasso throwing out useless medical markers, or Dropout giving a neural network selective amnesia so it builds better architecture, or Netflix clustering your movie tastes with strangers. Regularization is the pursuit of elegant simplicity.
It is about finding the true signal in a world entirely overwhelmed by noisy data. And, this raises an important question, stepping away from the math for a second and looking at how this applies to us.
Oh, lay it on us.
We've been talking about the math in the text all day, but applying this to our own lives raises a wild thought.
I'm ready.
The source notes that from a Bayesian point of view, regularization is simply imposing certain prior distributions on model parameters.
Prior distribution.
We are mathematically telling the AI what we expect the world to look like before it even looks at the data. We enforce a prior belief that the world is inherently simple or sparse or clustered.
Oh, so we are hard-coding our assumptions into the machine so it doesn't get overwhelmed?
Exactly. So if our most advanced, logical, objective supercomputers absolutely require mathematically enforced priors and penalties to prevent them from drawing absurd, overly complex conclusions from noisy data,
Yeah.
are human assumptions actually just a biological form of regularization?
Oh, wow.
Right? We often think of our cognitive priors, our mental shortcuts and assumptions as flaws. But are those biological priors the only mechanism keeping our brains from being completely paralyzed by the infinite noise of everyday life? Are
Uh,
we just biologically regularized machines?
that is a heavy, fascinating thought to leave on. Maybe our brains are constantly applying early stopping so we can get out of bed in the morning without overanalyzing the atomic structure of the floor.
I know, I definitely use early stopping before my morning coffee.
To everyone listening, thank you for joining us on this deep dive into the mathematical engine of AI. Next time you're studying for a test, remember, don't memorize the practice questions, learn the overarching concepts, stay curious, embrace simplicity, and we'll catch you on the next deep dive.